A short review of Calculus 1 skills. This presentation should show some of the basic skills that you should have learned in your Calculus 1 course. We'll start with some review of the basic differentiation rules. You should have seen all of these rules as part of your first semester calculus course. And so I'm just displaying them here as review. The derivative, okay, so d by dx, recall that this means the differential or the derivative with respect to x. So x is our independent variable. So if I want to find the derivative with respect to x of a constant, that's 0. The derivative of a constant being multiplied by some function is the constant times the derivative of the function. So recall that notation. If our original function is f of x, then its derivative can be described as f prime of x. The derivative of a sum or a difference of functions is the same as the sum or the difference of the derivatives of functions. So when we're adding or subtracting terms, the differential goes across, okay, and keeps it as addition or subtraction. However, if we have a product or a quotient, remember we have special rules for the product and quotient of functions. If we're multiplying functions, we have this product rule, which says that the derivative of f times g is f times g prime plus g times f prime. All right. Now, I will often, just the way I originally learned it, I'll often write the second term as f prime of x times g of x. So that's just something to be aware of. I'm still following the rule. I'm just not writing the factors in the same exact order, and that's okay. The quotient rule: the derivative of a quotient of f over g is g of x times f prime of x minus f of x times g prime of x over g of x squared. All right, and there's a little way to remember this. A mnemonic device. The low function, low d high minus high d low. All right, over low low. All right, that's the device. I still use that when I'm remembering when I have to use the quotient rule. So take the low function times the derivative of the high function minus the high function times the derivative of the low function over the low function, the low function squared. The quotient rule. We have the chain rule, and the chain rule tells us that if we have a composition, right? If we have a composition of functions, we sort of differentiate the outside function, leave the inside function alone, right? This is the inside function. Leave the inside alone, and then we should have the derivative of the outside function, of the inside function, the g prime of x. And we have our basic power rule. So if we're differentiating x to the nth power with respect to x, we can use the power rule. We kind of bring down the exponent. We still have the x, and then we decrease the exponent by 1. But this is only true if n is a number, a real number. And then we have our rules for our trigonometric functions. The derivative of the sine is cosine. The derivative of the cosine is negative sine. The derivative of tangent is secant square. The derivative of the cotangent is negative cosecant square. The derivative of the secant is secant tangent, and the derivative of the cosecant is negative cosecant cotangent. Now let's see some examples where we apply these rules. Differentiate y equals 5x cubed plus 3 tangent x. All right, so then the derivative, I'll use the notation y prime here. The derivative would be d by dx of 5x cubed plus d by dx of 3 tangent x. All right, so I used the sum, right? At a sum of functions, I can sort of break that apart. Now I have on each of those I have a constant being multiplied. 5 is a constant, 3 is a constant. So I can write this as 5 times d by dx of x cubed plus 3 times d by dx of tangent x. All right, now applying the derivative. The derivative of x cubed is 3x squared. So I have 5 times 3x squared plus 3. The derivative of tangent x is secant squared x. And so I can say that y prime is 15x squared plus 3 secant square x. F of x is equal to x to the 4th cosine x. Notice that this is a product of functions, so I will apply the product rule, with my first function being x to the 4th and my second function being cosine x. So then f prime of x, using the product rule, so remember that's the f g prime plus f prime g. That's the way I think of it, so that's the way I'm going to write it. So f prime of x, leave the first function alone, x to the 4th, times the derivative of the second function, negative sine x, plus differentiate the first function, 4x cubed, leave the second function alone, cosine x. So I'll write this as negative x to the 4th sine x plus 4x cubed cosine x. Differentiate s of t is the square root of t over t plus 1. So here I see this, this division, right? I see that division bar, so I'm immediately thinking quotient rule. And recall that the quotient rule is low d high minus high d low over low low. Additionally, I'm going to think of that square root of t as t to the 1/2 power. So then s prime of t low t plus 1, d high 1/2 t to the negative 1/2 minus high t to the 1/2 d low. The derivative of t plus 1 is just 1 over low square, t plus 1 square. Now let's rewrite this. I have that 1/2 t to the negative 1/2 times t plus 1. So I can write that term as t plus 1 over 2 times the square root of t minus t to the 1/2. That's the square root of t, and we still have the t plus 1 squared in the denominator. Now, we generally don't like fractions in fractions, so what I'm going to do is I'm going to get rid of this fraction by multiplying both numerator and denominator by that quantity, so 2 root t. So then s prime of t would give us t plus 1 minus, now the square root of t times 2 times the square root of t, we'd have a 2, and the square root of t times the square root of t is a t. So quite as big a fraction bar here. And then I'd have 2 root t by t plus 1 squared in the denominator. I can simplify the numerator sum by combining like terms, so I'd have negative t plus 1 over 2 root t by t plus 1 squared. Now, this is fine for me. Some people don't like this irrational factor in the denominator, right? So some people don't like that square root of t in the denominator, so we might multiply by square root of t over square root of t to rationalize the denominator. And so then I could write that s prime of t is root t by negative t plus 1 over 2t by t plus 1 squared. G of x is the sine of 3x squared. So notice we have a composite function here, right? I have a function, 3x squared, inside another function. So here, remember, we have to apply the chain rule. So then g prime of x, the outside function is the sine. The derivative of the sine is the cosine. So I'd have the cosine of the inside times the derivative with respect to x of that same inside. All right, so something like that. Now the derivative of, with respect to x of 3x squared is 6x. So then this is cosine of 3x squared times 6x. And normally we write this as, I'll write g prime of x as 6x times the cosine of 3x squared. So normally we put that algebraic term first, and then the, I should say factor first, and then the geometric factor. I should say trigonometric factor. Alright, so let's recall an application of the derivative. Determine the equation of the line tangent to y equals 8 sine square x when x is pi over 6. Alright, so the equation of the line. Alright, so to determine an equation of a line, I need a slope and I need a point. And if I have that, then I can write y minus y1 is m by x minus x1. That's the point slope form of the equation of a line. So let's figure out the point first. All right, so I need a point. Well, I know that we want it when x equals pi over 6. So if x is pi over 6, then y would be 8. Remember, sine square means, let's see, 8 sine square of pi over 6. So recall that sine square means that I would take the sine of pi over 6, find that result, and then square it. Now, from my trigonometry, the sine of pi over 6 is 1/2. So that's 8 times 1/4, which is 2. So if x is pi over 6, y is 2, so I have the point pi over 6, comma 2. Now let's figure out a slope. Alright, so recall that the slope is given by the derivative. So I'm going to find the derivative at x equals pi over 6. So let's first calculate the derivative. All right, so y prime, or dy dx. Well, let's see. Let me rewrite the function first. Let me think of this function. Y is 8 times sine of x square. Let me remember that that's really what that means. And so it looks like I'm going to have to use a chain rule here. So then y prime would be 8 times power rule 2 sine x, and then d by dx of sine x. There's the chain rule. So then I'd have 16 sine x cosine x. Now letting x take the value pi over 6, so y prime at pi over 6 would be 16 sine pi over 6 cosine pi over 6. So that's 16. The sine of pi over 6 is 1/2. The cosine of pi over 6 is root 3 over 2. And so this simplifies as, what, 4 times the square root of 3. And that's the slope. So putting that all together, I can write y minus y1, y minus 2 is m 4 root 3 by x minus pi over 6. And that's the equation of the line. They didn't ask for a slope-intercept form, so I'm going to just leave that alone. All right, so now we move into the other process, anti-differentiation or integration. So here's a table of indefinite integrals. And recall that if we have a if we're trying to find the antiderivative of a constant times a function, we are allowed to bring the constant multiple out in front. And if we have a sum or a difference, we're allowed to break up an integral over that sum or difference. All right, some basic rules. The antiderivative of a constant with respect to x, that's what, remember that dx we sort of say with respect to x. The antiderivative of the constant is the constant times x. And then remember we have a constant of integration for antiderivative, so that's what that plus c is. And then if we have a polynomial term, if we have x to the n, to find the antiderivative, we increase the exponent by 1 over that new exponent. And recall that this is only valid if n is not equal to -1, because that would give us a 0 in the denominator. And we'll see what happens, how we can deal with that in this course. What happens if we have just plain old 1 over x? How do we find its antiderivative? All right, and so then using our rules for what we learned about trigonometric functions, we can undo those. The antiderivative of sine x is negative cosine x. The antiderivative of cosine x is sine x. The antiderivative of secant squared is the tangent. The antiderivative of cosecant squared is the negative cotangent. The antiderivative of secant x tangent x is secant x. And for cosecant x cotangent x, we have negative cosecant x. And then we have the substitution rule. That says basically if we sort of see something that would be the result of a chain rule, we can use a substitution to make it easier to find the antiderivative. All right, so usually if we have, a lot of times, I shouldn't say usually, but we call, if we see a composite function, we will often call the u, that g of x, and we then have du is g prime of x dx. All right, so there's that g prime of x dx, and notice that in its place is now that du. And that's what we call the substitution rule. And we also learned about the fundamental theorem of calculus, and that was broken into 2 parts. And the second part says that if f is continuous on a closed interval ab, and big F is any antiderivative of f, then the integral from a to b of f of x dx is big F evaluated at b minus big F evaluated at a. So this gives us a way of calculating the integral, the definite integral of a function using its antiderivative. So let's see some examples. Here we have 2 expressions, and we're asked to evaluate. The first, we have the integral of x cubed dx. All right, so this is a very basic one. This we have x to the n. So the antiderivative is x to the n plus 1, so that's x to the 4th, over n plus 1, so over 4 plus a constant. I will frequently write this as 1/4 x to the 4th plus the constant. Remember, for these indefinite integrals, we can check our work by differentiating. So I can check what's the derivative with respect to x of 1/4 x to the 4th plus a constant. Well, the derivative of 1/4 x to the 4th, I'd have the 1/4 times, and the derivative of x to the 4th is 4x cubed, and plus the derivative of a constant is 0, and we're back to x cubed. All right, so that's good. Now, in the second exercise here, we have the we have the integral from 1 to 3 of x cubed dx. So here we take the we take any of the antiderivatives, and usually we use the most general, so I'm going to use the 1/4 x to the 4th, or I'll use that specific example. We take the 1/4 x to the 4th, that's an antiderivative of the x cubed, and we evaluate it from 1 to 3. Now, when we do this, we're allowed to take this constant, right? I can take this 1/4 outside. And so I can rewrite this as 1/4 and evaluate the x to the 4th from 1 to 3. And so then this becomes 1/4, and I'd have 3 to the 4th minus 1 to the 4th. So there's the f, right? This is the big F of b minus the big F of a. The antiderivative evaluated at b minus the antiderivative evaluated at a. And we have that 1/4. Whenever you have that constant multiple, you can bring that outside. So that's 1/4 of, what, 81 minus 1. That's 1/4 of 80. And so that's 20. Let's evaluate the integral x squared times the cosine of x cubed dx. So here I see a function. It's not any of my simple functions. So my only other technique is to try a substitution. And often we will try with the substitution on what's on the inside of the composite function. So here I see this cosine of x cubed. One idea is to try to let my substitution, let u equal the inside. It doesn't always work, but it's a good first try. So if u is x cubed, then du is 3x squared dx. Now if I look at this, I see the x squared and the dx, but I need a 3 as well. So what I do is I rewrite this. I have this integral, and I have the x squared cosine x cubed dx. But I say, well, wait a second, I need a 3x squared. So I bring the 3 in, but I just changed it fundamentally, right? I didn't start with 3x squared. I started with x squared. So what I have to do is I have to, in a sense, undo that 3 immediately by multiplying it by 1/3. Now I take this 1/3 and I bring it outside the integral. And so now I have 1/3 integral, and the 3x squared dx, there's the du, and the cosine x cubed, that's cosine u du. All right, so I have 1/3 integral cosine u du. The antiderivative of the cosine is the sine, so I have 1/3 sine u plus a constant, and then we put it back in the terms we started with. So I'd have 1/3 sine of x cubed plus a constant. Let's see another example with the substitution rule. So here I have the integral of cosine 4th theta times sine theta d theta. Okay, so remember that this really means the integral cosine theta to the 4th times sine theta d theta. And so again, if I think, well, I'm going to try the inside as my substitution. So I'm going to let u equal cosine theta. Well, if u is cosine theta, then du is negative sine theta d theta. And I see that I've got the sine theta d theta, I just need a negative. So I bring in a negative. Well, I've got to undo that negative. I bring in another negative. I'm going to put it outside, because that's just a negative 1. I'm just multiplying by negative 1s. So I can bring that negative 1 outside. So I'd have negative integral cosine theta, that's u, so u to the 4th, and then I have negative sine theta d theta, that's du. The antiderivative of u to the 4th is is 1/5 u to the 5th, so I have negative 1/5 u to the 5th plus a constant, and so I'll write negative 1/5 cosine 5th theta plus a constant. The integral from 0 to 1 of 2x plus 1 to the 9th dx. Alright, now in this one, maybe in pre-calculus, you learned a way to expand 2x plus 1 to the 9th, using Pascal's triangle, possibly. It's messy. It would work, though. We could expand that whole thing and find the antiderivatives and do all that. But instead, what I'm going to do is I'm going to use a substitution. So if I let u equal 2x plus 1, then du is 2 dx. So if I'm going to switch over to u's, I can do that. I've just got to be careful, though. I've got to also switch my limits of integration. All right, so if x is 0, u would be 2 times 0 plus 1, u would be 1. And if x equals 1, u would equal 2 times 1 plus 1 is 3. All right, I need du to be 2 dx, so I need to put a 2 inside. I need a 2 dx, which means I'll need a 1/2 on the outside. 1/2 times 2 is 1. And so I can rewrite this as 1/2 integral from 1 to 3 of u to the 9th du. So notice how I've changed the limits of integration as well. And so then this becomes 1/2. Now u to the 9th, the antiderivative is 1/10 u to the 10th. And I'll need to evaluate that from 1 to 3. Now I don't need to change back to x's here with this definite integral. I can keep it in terms of u as long as I change my limits of integration. And remembering that I can bring that 1/10 outside, this is 1/20th, and I have u to the 10th from 1 to 3. So this becomes then 1/20th of 3 to the 10th minus 1 to the 10th. And I don't know, 3 to the 10th is some crazy number. So my calculator shows this to be 1/20th of, let's see, 3 to the 10th is 59,049. 1 to the 10th is 1. That one's easy at least. And so I'd have 1/20th of 59,048. And so this ends up being 2,952.4. Alright, let's look at an application of the integral. Here we're asked to determine the area under y equals sine x between x equals 0 and x equals pi. So let's understand what we're asked for here. If I were to draw y equals sine x, okay, so recall that sine x has a period of 2 pi and an amplitude of 1. And so we get a curve. This is something we learned in trig. We get a curve that does this roughly. And so the area between and here's pi, I should say. The area under y equals sine x between 0 and pi, we want to know, what is that space right there? What is that shaded region? And this area is defined as the integral from 0 to pi of sine x dx. So then this area would be, well, the antiderivative of sine is negative cosine. So I'd have negative cosine x from 0 to pi. I can bring that negative out if I'd like. And so then the area would be negative. And let's see, I'd have cosine of pi minus cosine of 0. Alright, so I'd have negative. Now the cosine of pi is negative 1 minus the cosine of 0 is 1. And so then the area would be the negative, and negative 1 minus 1 is negative 2. And so then the area under that curve is exactly 2 units. Or I should say square units, but area is 2. Determine the area enclosed by y equals x squared and y equals 4x minus x squared. Alright, it's always a good idea to maybe sketch this to see what we're looking at. Y equals x squared is my basic parabola opening up. So there's y equals x squared. Y equals 4x minus x squared. I know that's a parabola opening down. Also notice I can write this as x by 4 minus x, so I know it has x-intercepts at 0 and 4. Alright, so then I have 0 and let's just say 4 is over here somewhere. There's 4, and so I'd have a parabola opening down with those x-intercepts. I get something like this. And so the area we're talking about is this shaded region right here. I want to find that area. Well, I need to know where these two curves intersect. So to figure out where they intersect, I solve the simultaneous equations y equals x squared and y equals 4x minus x squared by setting them equal to each other. So I'd have x squared equals 4x minus x squared. So I can write this as 2x squared minus 4x is 0. I can use some factoring here. That's 2x by x minus 2 is 0. And so from algebra that implies that x equals 0 or x equals 2. So now I can finally write an integral. Alright, and so my integral would be from 0 to 2. I'm going to write that the area is the integral from 0 to 2, and I'd have the upper function minus the lower function, and I would evaluate that with respect to x. So the integral is from 0 to 2. The upper function in this case is what I drew in blue, so that's the 4x minus x squared. Minus the lower function is just x squared, and I have to evaluate that whole integral with respect to x. And so then this simplifies as the integral from 0 to 2 of, let's see, we'd have a negative 2x squared plus 4x dx. And so then the area is, using the antiderivative, this would give us, what, negative 2/3 x cubed plus 4x squared over 2 plus 2x squared. And we need to evaluate that from 0 to 2. Alright, so I'm not going to split this up. I'm just going to do some direct substitutions now. So let's see, I'd have negative 2/3 of 2 cubed plus 2 by 2 squared minus negative 2/3 of 0 cubed minus 2, plus 2 by 0 squared. And notice that that whole term goes to 0, which is nice. So let's see, negative 2/3 times 8, that's negative 16/3. plus 2 times 2 squared is 8. Now 8 is the same as, what, 24 thirds? And so then the area is 8 thirds. Alright, that concludes this review. I hope it gave you some quick reminders of what some of the skills you learned were in the previous course. We're going to be using these throughout this course, so if you need to brush up on some of these, please do some reviewing and be prepared for the rest of the course.